studied lots of things this year so far. So we have studied things like what did we start with? We started with velocity, right? And then to get velocity, we looked at like a change in position or a position versus time graph, and a change in position versus time gave us velocity. We also studied this whole, like, well, we have our velocities and time, and maybe we have a velocity that's constant, and then that velocity changes, and then maybe it's constant again or something like that. What's happening during this changing time right there? There's an acceleration when there is a change in velocity over change in time. Okay? So, and we looked at graphs meaning different things. So with our velocity time graph, it was really super powerful, meaning we could get lots from it. So if you had a velocity time graph like this, you could find the acceleration would be the slope of the line. And then you could also find the change in position. How would you find the change in position if you had that velocity time graph? Do you remember? The area under the curve. That's right. So, and if you were going to do the area under the curve, you would do the area of the triangle plus the area of the rectangle. So that would be the area. So a lot of times the slope means something and the area means something. Then we looked at things like forces and energy. We've also studied forces. And you wanted to tell me all semester that F is equal to ma. Very good. And we learned that it's really the sum of all the forces acting on the object is equal to m times a, mass times acceleration. And we even graphed force and distance. Do you remember what you get when you have a force that's acting on an object for a particular distance? Work. And so the area under that graph was the work done by that force. And work causes a change in energy, so work and energy are synonymous. Now, let's look at this F is equal to ma bit a little more in depth. So, A, how do you find acceleration? By definition, it's the what? Change in velocity over change in time. So, what if I made a substitution and said, all right, well, the net force then must be equal to m times delta v over delta t. And maybe the net force is a force. Maybe the net force is a force that's acting on an object. Maybe we've got a box sliding across the ice. So here's my icy surface, and you're pushing on it with a force F. So the net force on it in the x direction would just be F. There's no friction, nothing like that. So then F would be equal to m delta v over delta t. If you have this one force causing a change in velocity. So could I write this as F times delta t is equal to m delta v? Is that legal? That force times time should be equal to mass times a change in velocity? Okay. So force times time. Now I'm going to just try to make a kind of make an analogy here. We had that work was equal to force times distance, and you just told me that if I take the force versus distance graph and we had a constant force acting on it, then the area under this would be work. So force times change in time. Could I graph force and time? Sure, a force can act on an object for a particular amount of time. And maybe that force is a nice constant force. So if I take force, that's like the height here, F, and I multiply it times D, from the graph, geometrically, that's the area. If I have force, which is like the height here, and the change in time, which is this, whatever that delta T is, would the area be equivalent to whatever F delta T means? Yeah. What does that mean? We call that the impulse. The impulse. So think about the word impulse. When I think of impulse, I think of when I am at the grocery store and I'm leaving and I'm like, oh, I'm going to grab some gum, and oh, that magazine looks interesting, or oh, I need some chapstick. Have you ever made those impulse purchases? The impulse aisle? Okay, so a lot of times we associate the word impulse, like we have friends that might be impulsive, right? Maybe that's a characteristic of someone's personality, that they make choices quickly. There's that time, like doing something over time, that is kind of that connotation with impulse. So now for work, the unit was the force, which would be newtons, times the distance, which would be meters. So what is the unit for this force delta T thing? Second, that's right. So Newton for force in seconds, we get Newton seconds. So completely different unit, completely different meaning. I'm just trying to draw an analogy that we used area once. What would area now give us? So, impulse, that's right. Now, what if I were to draw a velocity graph to match that force? So that force was constant. So what can you tell me about the acceleration? Constant. What would a constant acceleration look like on a velocity time graph? Probably something like that. At a positive force, so I'll have a positive acceleration. So could you find the change in velocity? Sure. Final velocity minus initial velocity. So we could find the change in velocity. If this is a mass that we're pushing on, so remember, go back up here to my analogy up here. We have the mass m that we've applied this force to. If I have the change in velocity and the mass, could I find F delta T? Which is called what? Impulse. So you can find impulse by using the force and the time that force is acting, or the mass and the change in velocity of the object. Now those are kind of basic interactions. So let's look at one that would be a little bit different. What if our force is not constant? The force versus time is not constant. So maybe something like that. Fairly simple, but still not constant. Could you find the impulse? Yeah, you could find the impulse for a particular time interval. So that would be your delta T. This would be the maximum force would be your height there, F. So how would you find the impulse here? It would be 1/2 the base times the height. So still the area. The area under, still the area. No, it's not curvy, but usually it's called the curve, the area under the curve. Now, for those of you that are in a fancy math class, what's the fancy name for area under a curve? The integral. So this means the integral. So for those of you not in a fancy math class, I don't want you to be afraid of the word integral. It just means area. And it's hard to do if you have curvy, truly curvy functions. But that function looks pretty straight, so you could find the area just using geometry. So what would the velocity time graph of this guy look like? Is the force always positive? Is the force always constant? So the acceleration, if F is equal to ma, so force is proportional to acceleration. If the force is positive, the acceleration is positive. If the force is increasing, then so force is proportional to the acceleration. So how should my graph look? Oh yeah, it's going to be like a curve. Doesn't the slope of the velocity time graph give us acceleration? So if our force is increasing, our acceleration is increasing, therefore the slope of the line at any point is increasing. Okay? Now, what if we had something even crazier? What if we had a force versus time graph where the force was more like for a collision? So think about when two things collide. Think about it in slow motion. If you were to watch have you seen the videos of like a crash test? And in slow motion, the car approaches the wall, and what does it do? It goes in and it begins touching, okay, until it's like crumpled and all the way up against the wall, and then usually it does what? Bounces back, recoils. So the force goes from being this initial touch force when they first come in contact with each other to this maximum where it's like crumpled car to being bounced back off. So the force goes from something kind of small to something kind of big, and then when it bounces back off, it's kind of like rewind. So collision may look something like that, where the force goes from the initial force when they begin to touch each other until it's squished, and the force is really big. Could you find the impulse there? Yeah, you could find the area. The impulse is still the area, which is the easy way to think of an integral. Just don't want you to be afraid of that word. Oh, so what would my velocity graph look like maybe? Velocity versus time. Now remember, force is proportional to acceleration, and acceleration is the change in velocity over change in time. So initially, is our force positive? Sure. At the maximum force, is the force positive? Well, the force would not be zero. These are all positive forces. Positive, 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 positive. So we still have a positive force there. Do we still have a positive force at this time? Yeah. At this time? Yeah. So if I have a positive force, then what's my acceleration? Positive or negative? Positive. So tell me about my change in velocity. It'd also be positive. So maybe this is a car that's moving towards a wall, and the wall is maybe to the left. So I need to make it so it's going to hit the wall. Something like that. Actually, I need to make it a little. So does this overall have a positive slope? Okay, so overall, my acceleration is positive. That does not look right. Let's fix that up. How about we have overall a positive acceleration? We have a positive force the whole time, but the slope is going to be changing all the time. And we have a maximum slope at this time right here, t, which would be this time right here, t. I didn't draw them parallel to each other like I should have. So I could have drawn it negative. I could have drawn it positive because I don't know my initial velocity. So this was just a possible graph because it maybe bounced off. You could have the interaction cause the velocity to go from some positive to some greater positive like that, where this still would be T mid. I was just giving you a for instance. Like if you collide with a wall.
Yeah, but if we were to look at the example, the force example from before, where it was a cusp.
Yep, this
right
one.
There,
Yep.
Wouldn't the velocity graph right under it be, if you reflect it over the x-axis, wouldn't that be a representation of?
So my question for you then is, if you have the data for a force versus time of a collision, so a collision that occurs, and so there's no force, and then suddenly, wham, there's a force like that. Could you verify that the force times the change in time, the area under the integral, is equal to the mass times the change in velocity if you also had the velocity versus time graph? So you had this graph. You should be able to see if this is equal to that if you have this graph and that graph. So that's what we're going to do today.